In this video, we're going to consider variable forces, that is, forces whose magnitude changes. And one of the most famous of these is called a Hooke spring force. This is the force applied by an idealized spring upon an object. Now, what's neat about this is that many systems that don't look like springs, for instance, the interactions between atoms inside a crystal or electrical circuits, behave as if there are these Hooke springs. So it has great applications in a wide range of fields of engineering and science. The Hooke's law, as it's called, was found by Robert Hooke, who was a contemporary of Isaac Newton, although they were certainly not friends. What it says is that if you take a block and attach it to a spring and you stretch that spring, then the spring will apply a force, and that force will try to undo this stretch. Furthermore, the further you pull the block, the harder the spring will pull back against you. To put it more mathematically, it says it's directly proportional to the amount that you stretch or compress the spring. This means if you double the distance you stretch the spring, the force doubles. If you triple the distance you stretch the spring, the force triples. And one way to do this is to plot it. So if this is x, then the force, if you go in a positive direction x, will be a negative number, and it will fit a straight line. This is what this equation means. It plots a straight line. That's what this directly proportional to do. And the fact that it opposes the stretch means that if you go positive x, then the force is in the negative direction. If you compress it by going this way in the negative x, then the force will be in the other direction, that is positive. So it's got a negative slope, if you would. Now, you can actually put all of this into an equation, which is called Hooke's law. It says the vector force that we just talked about is equal to minus kxi hat. Now, usually we just talk about the magnitude. So the magnitude is just k times x, where k is called the spring constant. The minus sign that goes with the I hat is just to indicate the direction, opposes the displacement. Since we draw free body diagrams and put our plus and minus signs when we do that, then we usually just use this, like we do mg for weight, and we use the arrows to take care of the minus signs. In more advanced classes in college, when people put things called differential equations together, they actually like to leave these I hats and write it as vectors. But you will find it of no use really in this course. So instead, we'll just think of the force as having a magnitude kx, and the direction is given by the arrow that we draw on the free body diagram. Now, one thing about this formula, it assumes a very special place for x equals 0. I usually tell you that you are in charge of your axis set. Not anymore. If you're going to use the formula the Hooke derived for you, then the x equals 0 location, that is your origin, has to be the place where the string is unstretched. If you put it anywhere else, the formula doesn't work, and you have to derive your own formula. So, this is a very small giving up of freedom in order to take advantage of the fact that we have a formula to use in our problems. Let's talk about the spring constant. The spring constant contains all the information about how the spring was actually made. My great-grandfather made buggy springs, and he would heat these buggy springs in a forge, and he would bend them, and then he would take the steel and stick it into a sand and oil mixture and cool it. And what it was said was that you had to heat it until it was cherry red, and then you had to quench it in this oil sand bath for so many seconds afterwards, and that made a nice spring. But whether what you see as cherry red or what he saw as cherry red might be different. You get a totally different type of spring. All of that information about how to make it and that skill is contained in the spring constant. If you have a big K, then it means you have a very big spring. big K. If you have a small K, it's more like a dart gun type of spring, the type that you can bend and stretch easily. The big K is more like a giant car spring. Right? So a big value of K means a very stiff spring. A small value of K means a very weak spring. Now what is the K? Well, if you just plot the magnitude, let's say, of F against X, then for one spring you might get a straight line like this. And for another spring you might get a straight line that looks like this. The slope is your K. And in fact, we may do a lab in which you actually measure the spring constants of different springs by hanging masses on them and plotting it to get the slope of the line. Are any real springs actually Hooke springs? Well, yes, provided you don't stretch them too much. If you stretch them too much, the springs basically will get stretched out and they no longer act like a good spring. Now, why does this actually work? Well, the reason for this is that if you take any type of force, let's say that the force looks something like this. Certainly not a straight line. But if you consider any point, let's take this point right here, and you only allowed it to go just a little bit to either side, you could fit that with a straight line. If you were at this point here, then you could let that fit as a straight line. This value as a straight line. This as a straight line. This as a straight line. So about any starting point that you choose a material, you can consider small displacements, small changes as being a straight line. If you make the chart change too big, whoops, sorry about that. If you wanted to run the thing from, say, here over to here, fitting a straight line, not doing a very good job drawing, fitting a straight line, from here to here, still fits pretty good. But if I wanted to try to fit all the way to there, it wouldn't. And if I wanted to fit to there, it wouldn't. But if I only was to adjust it so it worked in this region, then a straight line is a pretty good fit. So if you don't stretch or make a system move too much, it can appear to act like a spring. When they do that in engineering world, they call that linear analysis. So electrical engineers have linear circuit analysis. Mechanical engineers have linear structural analysis. All sorts of classes. This means that you are treating the system as not having too big of a shift, and so you can fit it with a straight line, even though the whole force is probably not a straight line. Now, the next thing to do is get back to our discussion about work. So let's go back to our problem of finding the work done by a Hooke spring. So let's assume we had a spring here. Oops. And I've got a spring attached to some sort of a block. And I'll let that block sit like this. And I'm going to pull that block to some new location. So now it's over here at some value of x. And the spring is now going to pull back in that direction. Well, the force will be in the negative direction. So we know what it looks like. It looks like this. So you pull it some distance x. And it has some value minus kx. And if we pull it from 0 over this away, going in this direction, where this is x, the work done is found by the area under the curve, which is this. So what is the area? The area would be 1/2 base times height. Well, let's see. The area would be 1/2. The base is a positive x. The height is not positive. In work diagrams, you can have negatives. This height here is minus kx. This gives us minus 1/2 kx squared. And this is equal to the work. So the work on this force can be found by simply plotting a force versus position diagram, and we don't have to add up little rectangular boxes. We recognize this shape as a triangle and we can find it. Now notice the way I did this. If you go this direction, it's a positive x. You could also have the object already stretched and we could let it become unstretched. If you did that, the block would pick up speed. This distance would be a minus x. You get a minus times a minus, you get a positive work. Remember, negative work implies slowing down. Positive work implies speeding up. This object slows down as spring is stretched. So this graphical interpretation, this work equal area, is very useful in these variable force problems.